Hello, everyone. In this section, we will introduce two diode applications in electronics: DC restorer circuits and voltage doubler circuits. The circuit shown here is a DC restorer circuit. It can be made with a capacitor connected in series with a diode. The output voltage, VO, equals the input signal VI plus the capacitor voltage VC. In other words, the polarity and value of VC determine how the input waveform is shifted. To simplify the analysis, we first assume that the diode is ideal. That means it acts as a short circuit under forward bias and as an open circuit under reverse bias. We also assume that the capacitor initially stores no charge, so its initial voltage is 0 volts. These assumptions are the starting point for the circuit analysis. When the signal source is connected at t equals 0 seconds, the input signal Vi is negative 10 volts during the interval from 0 to t1. At the instant the source is connected, the diode is forward biased and behaves like a short circuit. Therefore, a large diode current, ID, flows and charges the capacitor. Since the current flows through the capacitor from the right side to the left side, the right plate becomes higher in potential than the left plate. With the voltage polarity defined in the circuit, Vc becomes a positive voltage. After the capacitor charges to Vc equals 10 volts, the diode no longer conducts, so ID becomes 0. The circuit then reaches a steady state. At this moment, the output voltage is VO equals Vi plus Vc, which is negative 10 volts plus 10 volts, equal to 0 volts. If the charging time is much shorter than T1, then the output voltage remains approximately 0 volts throughout the interval from 0 to T1, as shown in the waveform. Next, during the interval from T1 to T2, the capacitor voltage from the previous steady state is still Vc equals 10 volts. When Vi changes to positive 5 volts, the output voltage immediately becomes VO equals Vi plus Vc, which is 5 volts plus 10 volts, equal to 15 volts. At this time, the diode is reverse biased and acts as an open circuit. Since there is no current path to change the charge stored in the capacitor, Vc remains unchanged. Therefore, during the entire interval from T1 to T2, the output voltage stays at 15 volts. Then, during the interval from T2 to T3, the capacitor voltage is still Vc equals 10 volts. When Vi changes back to negative 10 volts, the output voltage immediately becomes VO equals Vi plus Vc, which is negative 10 volts plus 10 volts, equal to 0 volts. The diode is still not forward biased, so it remains non-conducting. Since there is no current path to change the capacitor charge, Vc remains unchanged. Therefore, during the interval from T2 to T3, the output voltage stays at 0 volts. Finally, the same process repeats cycle after cycle, as shown in the waveform. In simple terms, this circuit shifts the entire input waveform upward so that the output becomes a positive polarity waveform, while the waveform shape itself remains unchanged. This means that a fixed DC voltage offset has been added to the original signal. For this reason, the circuit is called a DC restorer. Now, what happens if we use the same circuit but reverse the direction of the diode, as shown in the figure? We can analyze it in the same way. When the signal source is connected at t equals 0 seconds, the input signal Vi is positive 5 volts during the interval from 0 to T1. At the instant the source is connected, the diode is forward biased and behaves like a short circuit. A large diode current, ID, flows and charges the capacitor. This time, the current flows through the capacitor from the left side to the right side, so the left plate becomes higher in potential than the right plate. With the voltage polarity defined in the circuit, Vc becomes a negative voltage. After the capacitor charges to Vc equals negative 5 volts, the diode no longer conducts, so ID becomes 0. The circuit reaches a steady state. At this moment, the output voltage is VO equals Vi plus Vc, which is 5 volts plus negative 5 volts, equal to 0 volts. If the charging time is much shorter than T1, the output remains approximately 0 volts during the interval from 0 to T1, as shown in the waveform. During the interval from T1 to T2, the capacitor voltage from the previous steady state is Vc equals negative 5 volts. When Vi changes to negative 10 volts, the output voltage immediately becomes VO equals Vi plus Vc, which is negative 10 volts plus negative 5 volts, equal to negative 15 volts. The diode is reverse biased and acts as an open circuit, so there is no current path to change the charge stored in the capacitor. Therefore, Vc remains unchanged, and the output stays at negative 15 volts throughout this interval. During the interval from T2 to T3, the capacitor voltage still remains at negative 5 volts. When Vi changes to positive 5 volts, the output voltage immediately becomes Vo equals Vi plus Vc, which is 5 volts plus negative 5 volts equal to 0 volts. The diode is still not forward biased, so it remains non-conducting. Since no current path changes the capacitor charge, Vc remains unchanged. Therefore, the output remains at 0 volts during this interval. Finally, the waveform repeats in the same way. In simple terms, reversing the diode shifts the entire input waveform downward so that the output becomes a negative polarity waveform while the waveform shape remains unchanged. We can now compare the output waveforms of the two DC restorer circuits. The diode direction determines whether the waveform is restored upward or downward. A simple way to remember this result is, when the diode direction points upward, the whole waveform shifts upward toward the positive direction. When the diode direction points downward, the whole waveform shifts downward toward the negative direction. Next, what happens if we add a resistor R in parallel with the diode, as shown in the circuit? When the signal source is connected at t equals 0 seconds, the input signal Vi is negative 10 volts during the interval from 0 to T1. At that instant, the diode is forward biased and behaves like a short circuit, so a large diode current, ID, flows. In addition, the resistor R also has a current, IR. Both ID and IR contribute to charging the capacitor. Since the current flows through the capacitor from the right side to the left side, Vc becomes positive. After the capacitor charges to 10 volts, the diode stops conducting, so ID becomes 0. The resistor also has no voltage difference across it, so IR becomes 0. The circuit reaches a steady state, and the output voltage is Vo equals negative 10 volts plus 10 volts, equal to 0 volts. If the charging time is much shorter than T1, the output is approximately 0 volts during this interval. During the interval from T1 to T2, the capacitor voltage at the end of the previous interval is Vc equals 10 volts. When Vi changes to positive 5 volts, the output voltage immediately jumps to Vo equals Vi plus Vc, which is 15 volts. The diode is now reverse biased and open, so ID is 0. However, the resistor R has the output voltage across it, so IR equals Vo divided by R. This current provides a discharge path for the capacitor. As the stored charge in the capacitor decreases, Vc also decreases with time. By the time T reaches T2, the capacitor voltage has dropped by Vr, so the output voltage becomes 15 volts minus Vr as shown in the waveform. During the interval from T2 to T3, the capacitor voltage at the beginning of this interval is 10 volts minus Vr. When Vi changes back to negative 10 volts, the output voltage immediately becomes Vo equals negative 10 volts plus the quantity 10 volts minus Vr, which equals negative Vr. At this instant, the diode becomes forward biased and starts to recharge the capacitor. The charging continues until Vc returns to 10 volts. At that point, Vo becomes 0 volts and the diode no longer conducts. The output waveform shown on the right represents this recharging behavior. Finally, the same process repeats cycle after cycle. In simple terms, the circuit still shifts the input waveform upward, but because the resistor R exists, the capacitor charges and discharges over time. As a result, Vc is no longer perfectly constant, and the output waveform becomes slightly distorted. Now we compare the DC restorer without the resistor and the DC restorer with the resistor R. The presence of R makes the capacitor repeatedly charge and discharge. When the input signal changes by Va, the output Vo also changes by Va. However, because Vc decreases during capacitor discharge, a negative portion appears in the output waveform. After that, the capacitor charges again, and the negative output voltage rises back toward 0. After introducing the DC restorer and the peak rectifier, we can compare these two circuits. As shown here, both circuits are made from a capacitor and a diode, but their positions are different, so their functions are different. A DC restorer shifts the entire waveform to one polarity without changing its shape. A peak rectifier stores the maximum amplitude of the signal as a nearly constant DC output. and the output polarity depends on the diode direction. Next, we connect a DC restorer and a peak rectifier in series, as shown in the circuit. When a sinusoidal input first passes through the DC restorer, the whole waveform is shifted upward by VA, forming the signal VO1. Then, after VO1 passes through the positive peak rectifier, its maximum positive voltage, which is 2 times VA, is held as a stable output voltage, VO2. Therefore, the final output voltage is higher than the original input amplitude VA. This circuit is called a voltage doubler. Therefore, the upper circuit shown here is the voltage doubler we just introduced. When an AC sinusoidal signal is applied, the circuit produces a positive output voltage that is approximately twice the input amplitude. But what happens if both diode directions are reversed, as shown in the lower circuit? In that case, the DC restorer diode points downward, so the sinusoidal waveform is shifted toward the negative direction. The output of the DC restorer, VO1, becomes an entirely negative waveform. Its most negative value is negative 2 times VA, and its most positive value is 0 volts. Then the signal enters the peak rectifier. Because the peak rectifier diode is reversed, it holds the most negative voltage value as the output. Therefore, the final output is a stable negative 2 times VA. This is a negative polarity voltage doubler. The upper circuit is a positive voltage doubler, and the lower circuit is a negative voltage doubler. If the two diodes inside the voltage doubler are not arranged with the anode of one diode connected to the cathode of the other, for example, if they are connected anode to anode or cathode to cathode, the final output becomes 0 volts. You can follow the same signal analysis process to draw the waveforms and verify this result. That concludes the introduction to DC restorer circuits and voltage doubler circuits. Please look forward to the next lecture. See you next time. Bye-bye.